We now start module 3 of chapter 4, where we will be talking about diagonalizability conditions. We have already seen necessary condition for diagonalizability of a linear operator and also a sufficient condition. Now we will see a necessary and sufficient condition, which will be in terms of algebraic and geometric multiplicities for eigenvalues. V is a vector space of dimension n over a field F. The theorem says that if T is a linear operator on V with distinct eigenvalues lambda 1, lambda 2 and so on up to lambda k, and if Bi is a finite linearly independent subset of the eigenspace n lambda I for every I from 1 to k, then their union B, that is B1 union B2 and so on up to Bk, is also a linearly independent subset of V. Let us prove this statement. Let us write Bi as the collection of vectors Vi1, Vi2 and so on Vini. So, each Bi is a subset of the eigenspace n lambda I and for I equal to 1 to k. Now, let us write this linear combination summation over I, summation over j, Aij, Vij is equal to 0, where Aij's are scalars in the field F. Let us write this linear combination, that is summation over j of Aij, Vij as Wi. So, we fix I here and let j vary over 1 to ni, and this we do for each I from 1 to k. Then from that previous line we see that W1 plus W2 and so on up to Wk is the 0 vector. We claim that each of W1, W2 and so on Wk is nothing but the 0 vector. So, suppose not, and if possible let Wi be non-zero for I in between 1 and m, and Wm plus 1 and so on up to Wk be 0. Then that sum reduces to this sum W1 and so on up to Wm is equal to 0. And what are W1 and so on up to Wm? They are eigenvectors corresponding to distinct eigenvalues lambda 1, lambda 2 etc. up to lambda m. Why? Because these Wi's are vectors in the eigenspaces. But then we have a non-trivial linear combination of these vectors W1 etc. up to Wm, which definitely contradicts linear independence of W1 and so on up to Wm. We have already learned that eigenvectors corresponding to distinct eigenvalues, they form a linearly independent set. So, that is being contradicted here. Therefore, we have to have W1, W2 and so on up to Wk are nothing but the 0 vectors, and hence all the scalars Aij's must be 0 for all I and j. Therefore, we have proved that the set B, which is the union of B1, B2 etc. up to Bk is linearly independent. Now, a very important theorem. Let T from V to V be a linear operator on the n-dimensional vector space V over F. We assume that the characteristic polynomial of T splits in F. So, let lambda 1, lambda 2 and so on up to lambda k be distinct eigenvalues of T. Then T is diagonalizable if and only if the algebraic multiplicity mi of lambda I is equal to the geometric multiplicity di of lambda I for every I. and secondly, if T is diagonalizable and if Bi is an ordered basis for the eigenspace n lambda I, then B, which is the union of B1, B2 and so on up to Bk, that is an ordered basis for V consisting of eigenvectors of T. Proof: suppose that T is diagonalizable. Let B be a basis for V consisting of eigenvectors of T. We intersect B with the eigenspaces n lambda I, and let us call that set B intersection n lambda I to be Bi. Let Ni denote the cardinality of the set Bi. Then Ni is less than or equal to Di for each I, because Bi is a linearly independent subset of n lambda I. And the dimension of n lambda I, which is the geometric multiplicity of lambda I, that is Di. We already know that Di is less than or equal to Mi. Why? Because the geometric multiplicity is less than or equal to the algebraic multiplicity. Therefore, we get this inequalities, that is n, which is equal to summation of Ni summation over I, which is less than or equal to summation over I Di, which is less than or equal to summation over I Mi, but summation of Mi's is again n, and therefore it follows that summation over I Mi minus Di is 0. But each of Mi minus Di is non-negative, and therefore each summand must be 0, because it is the sum of finitely many non-negative integers is 0. So, each summand is 0, and therefore Mi is equal to Di for each I. Conversely, suppose that Mi is equal to Di for all I equal to 1 to k. For each I, let Bi be an ordered basis for the eigenspace n lambda I. Then we know that their union, which we call B, that is B is B1 union B2 etc. up to union Bk, then B is linearly independent by the previous theorem. But the number of elements in the set B is summation Di, summation over I, which is summation Mi, summation over I, because we know that Mi is equal to Di, and summation Mi, summation over I is nothing but n. Therefore, B is a linearly independent set with n vectors, and therefore B is an ordered basis for the vector space V. And elements of B are nothing but eigenvectors of T, hence T is diagonalizable. Now we have seen a necessary and sufficient criteria for diagonalizability of a linear operator on a finite dimensional vector space V. And the criteria is in terms of algebraic and geometric multiplicities of the eigenvalues of the operator. Algebraic and geometric multiplicities are some positive integers associated to the eigenvalues of the linear operator. And we have proved that geometric multiplicity is less than or equal to the algebraic multiplicity for each eigenvalue. And it is definitely possible that the geometric multiplicity is strictly less than the algebraic multiplicity. And that is precisely the case when the operator is not diagonalizable, because the criteria says that the operator is diagonalizable if and only if two conditions are satisfied. One is that the characteristic polynomial splits in the base field f, and the second one is that the algebraic and geometric multiplicities for each eigenvalue should match. We will rewrite this criteria so that the criteria is more computable. What does that mean? It means that we will rewrite that criteria in terms of the rank of the matrices for the linear operator, and we know that rank can be computed using elementary row operations. And therefore, if we can compute rank, then we can apply that criteria to test diagonalizability. So, this is what you will see now, followed by some examples. This theorem tells us about the same criteria for diagonalizability, but written in a slightly different form. So, let T from V to V be a linear operator on the n-dimensional vector space V over F. Then T is diagonalizable over F if and only if both of the following conditions are satisfied. Condition 1, the characteristic polynomial chi t splits in the field F, and 2, for each eigenvalue lambda of t, the algebraic multiplicity of lambda is equal to the geometric multiplicity of lambda, which is the nullity of the operator t minus lambda I, and that is n minus the rank of the operator t minus lambda I. Well, you can see that it is nothing new. It is the same theorem written in terms of rank and nullity. But the merit is that this indeed makes the criteria computable, because rank is something that we can compute through the row reduced echelon form. And what is nullity of t minus lambda I? That is precisely the dimension of the eigenspace n lambda, and we know the nullity of t minus lambda I is n minus rank of t minus lambda I by the rank nullity theorem. Let us see some simple examples. The first one talks about the rotation operator t pi by 2, which we have seen a number of times, and we have already checked that t pi by 2 has no eigenvalue in R. Therefore, it is not diagonalizable over R. Why? Because the first condition of diagonalizability is not satisfied. Recall, the first condition was that the characteristic polynomial must split in the base field. In this case, the characteristic polynomial is t square plus 1, which obviously does not split in the field of real numbers. Another example, Let T be the linear operator on R3 defined by T of x y z is equal to x plus z comma y comma y. It is written in the column matrix form. Let us now test T for diagonalizability. Remember, we have to test two things. One is whether the characteristic polynomial of T splits in R, and secondly, we have to see whether the algebraic and geometric multiplicities of the eigenvalues match, or in other words, whether the nullity of the eigenspaces are exactly equal to the algebraic multiplicities of the eigenvalues or not. And how to compute nullity? Nullity is n minus the rank. So, n is 3 here because the vector space is R3, which is 3 dimensional over the real field, and rank we can compute either by converting the matrix into row reduced echelon form or by simple observation. So, the characteristic polynomial of the matrix A is the matrix for the operator T written in terms of standard basis vectors, and the characteristic polynomial is chi t of t, which is minus t multiplied by 1 minus t whole square. Therefore, we see that the eigenvalues are precisely 0 and 1, but 1 is repeated and repeated twice. So, the algebraic multiplicity of the eigenvalue lambda 1 is equal to 0 is 1. Now, since the algebraic multiplicity is 1, therefore, geometric multiplicity has to be the same as the algebraic multiplicity, because the geometric multiplicity cannot be less than 1. So, it has to be 1. So, the second condition regarding equality of algebraic and geometric multiplicities, it is satisfied for this eigenvalue 0. Now, we have to see whether the same condition is satisfied for the other eigenvalue, that is 1. Here we see that the eigenvalue 1 is repeated. So, the algebraic multiplicity of the eigenvalue lambda 2 equal to 1 is 2. Therefore, what are the possibilities for the geometric multiplicities? It could be 1 or 2. Consider the matrix A minus lambda 2I, which is A minus I, because lambda 2 is 1, and that is this 3 cross 3 matrix with first row 0 1 1, second row 0 0 0, and the third row 0 1 minus 1. Now, we see that there is the first column which is completely 0, and there are 2 more columns, and the last 2 columns are linearly independent vectors in R3. Therefore, we can say from this observation that rank of this matrix A minus I is 2. Hence, nullity of the matrix A minus I is 3 minus rank of A minus I, that is 3 minus 2, that is equal to 1. Therefore, the geometric multiplicity of the eigenvalue lambda 2 equal to 1 is 1. So, in this case, the geometric multiplicity is not the same as the algebraic multiplicity for this eigenvalue, and therefore T is not diagonalizable, since the second condition of diagonalizability is not satisfied. We have seen diagonalizability of a linear operator in detail. We first introduced concepts of eigenvalues and eigenvectors, and then the characteristic polynomial, and the necessary criteria for diagonalizability is that the characteristic polynomial must split in the base field. That means all the roots of the characteristic polynomial, which are nothing but the eigenvalues, must belong to the base field. And a very standard example which we have seen is the rotation operator by an angle pi by 2. That is a linear operator on R2, but it has no real eigenvalue and therefore it cannot be diagonalizable. On the other hand, we have also seen examples where the characteristic polynomial splits in the base field, but then the second part of the criteria is not fulfilled, which says that algebraic and geometric multiplicities of the eigenvalues must match. We have seen examples. So, if we want to test diagonalizability, then the steps are the following. First, we choose a basis for the vector space and write down the matrix representation of the linear operator. We know that the characteristic polynomial of the operator does not depend on the choice of basis of the vector space. So, we can calculate the characteristic polynomial from that matrix representation, which is determinant of A minus Ti if A is the matrix representation. And then we have to see whether the characteristic polynomial splits in the base field. And finally, after we have identified the eigenvalues, we have to verify whether their algebraic multiplicities are precisely n minus rank of A minus lambda I. That is the nullity of A minus lambda I, which is of course the geometric multiplicity. We will see one more criteria for diagonalizability in the next module, where we will define the concept of a minimal polynomial, and the last criteria that we will be talking about on diagonalizability would be in terms of factorization of the minimal polynomial.